Okay, so hello everyone. Today we have Mina Konakovic Lukovic from MIT, previously at EPFL. Mina is a Schmidt Science Postdoctoral Fellow at MIT, working in the computational fabrication group with Wojciech Matusik. Her research focuses on computer graphics, computational fabrication, 3D geometry processing, and machine learning, including architectural geometry and design of smart materials. She completed her PhD in the CS department at DPFL in Switzerland, advised by Professor Mark Pauli. And today she's going to talk about turning planar materials into curved structures. Go ahead, Mina.
Yeah, thanks a lot for the kind introduction. After your great introduction, Miri. So I'll just mention that this work was done when I was at EPFL. Now I'm a postdoc at MIT, as you already heard. So I'll just dive into the work then. So in this work, we were looking at structures that can be made from flat materials and then turned into curved shapes. And what we have discovered is that by trying to connect these kind of fabrication problems with the ideas from differential geometry, we not only get very nice tools and algorithms for designing such shapes, but we can really understand ahead of time what kind of shapes we can make with these materials. And when we think of flat materials, for example, a sheet of paper, they're often developable. And what developable means is that the material is thin and flat, and it can bend freely, but it cannot stretch. And this is, their developable surfaces have been studied quite a bit recently. They have been gaining interest from famous architects, but also a lot of work has been done in computer graphics community. For example, the work from Helmut Potzmann's lab, or the work from Eric and Martin Demain on origami. But these surfaces, although they look really impressive, they are still limited to what they can achieve. And why do I say limited? Well, let's look at this simple example. This is a plastic, or this is acrylic sheet that is developable. You can freely bend it, but you cannot stretch it. And if you want to approximate a shape that is as simple as a sphere that is doubly curved, or it curves in two directions at every point on the surface, you cannot do it with a developable sheet like this piece of plastic. So you can try to wrap it around, you can bend it around, but you cannot really make a sphere out of it unless you cut it and so on. So what we did is to insert a regular pattern of slits into the very same material. And now all of a sudden the material can also stretch. And not only that it can stretch, but it can also approximate doubly curved surfaces. And these cuts make the material from developable to become auxetic. So this brings us to the first topic of the day, which are uniform auxetic materials. And just to give you a brief explanation or the definition of what auxetic materials are, well, if you look at this material, their defining property is negative Poisson ratio. And saying things simply, that means that if you stretch the material in one direction, it will also expand in the other direction. So not like conventional materials or most of the things that we see around us, where, for example, the piece of clothing, you stretch it in one direction, it will shrink in the other because it has the positive Poisson ratio. But for auxetics, they have this non-intuitive behavior. When you stretch them out, they also expand in all directions. And these materials have been studied in many different fields. They are becoming more and more popular now in engineering, biomedical engineering, and so on. So for example, here we see a three-dimensional auxetic foam that when you stretch it, it also expands in all other directions. Then this material has become very popular, for example, in Nike labs, where they are now using it for shoe soles, but also ASICS is also using it for clothing and also for shoes, tennis shoes, and so on. BMW has studied it for their concept car, where you can adapt the shape of the car to be able to better fit to the ground based on the driving style and the terrain. And also in electronically actuated materials, for example, for art pieces, for fashion pieces, and so on. So these materials are popping out everywhere recently, but what they all have in common is that they're all limited to very simple geometry. So you can have them planar, you can have them cylindrical, or at most spherical, but not more than that. And our question in this work was, can we actually approximate any complex shape with such auxetic material? So for example, if I take this face of Max Planck as a target surface and I want to approximate it with a piece of sheet of auxetic material, how can I do that, and whether I can actually do it or not? And we started looking into material properties then to learn how to control it and how it behaves. So first we started cutting out different types of materials to become auxetic. So for example, the plastic that you already saw, aluminum, copper, leather. We even tried with cardboard and paper and pretty much anything that is thin and flat, but not stretchable. We insert a regular pattern of slits inside, and then we get the auxetic material. And we, for the purpose of mathematics and controlling it in the algorithm, we abstract it in the form of a triangular linkage, a regular triangular linkage that has this so-called Kagome lattice, where on the most left-hand side, it's just a set of equilateral triangles. Then when you start opening it, it forms this hexagonal opening that is the most right picture on the bottom. And that's the farthest it can go in this configuration. Am I frozen again?
Yes, unfortunately, you're frozen again.
Sorry.
We can hear you, but yeah.
Yeah, this is very weird. Maybe the PowerPoint is causing it, because I gave this presentation.
Can you advance the PowerPoint? We can see if it goes on, and
I
then
cannot
we'll
do
just hear
anything.
you.
It froze again. Okay. So what I can do, I can maybe try this, because I had troubles with PowerPoint before. I didn't have them with Keynote. Maybe I can try to run the presentation in Keynote and see if it breaks.
Okay, so you want to reset again?
Yes.
I'll pause the recording and we can try again.
Sorry.
Okay.
Okay, great. Yeah, so I'll continue where I stopped. So we tried different and we use this geometric abstraction in the form of regular triangular linkage. And now these materials have the global coupling in them. So if you try to stretch out one part of the material, it will also affect the other side of the material as well. So if you really want to approximate a complex shape like the head of Max Planck, for example, and you take this sheet of auxetic material, you just try to wrap it around manually without any knowledge or guidance, you will in most cases fail badly because of this global coupling happening in the material. So imagine you have thousands of these triangles and they're all affected by each other by pulling in different regions. So you cannot just simply try to wrap it. You can do the trial and error forever, but it may not work for complex surfaces. So we looked into the material behavior in more detail. And what we have noticed is that this deformation is actually isotropical. So when we stretch the material out, it scales isotropically. And this led us to connect it to conformal geometry. And just to give you a brief overview of what conformal geometry is and why we care about it and why we find it related to this material. So conformal geometry or conformal mapping is a transformation that allows local rotation and uniform scaling, but not shearing. So you cannot have shearing happening in your deformation. In other words, conformal mapping preserves angles, but not lengths. And we can characterize conformal mapping by a local scaling factor. And in this transformation example on the right, for example, you can see that these squares preserve their 90-degree angles, but the size of the squares can uniformly scale. So the edges can scale up or down. And now, since our goal is to model curved objects from flat materials, we want to establish a relationship between the local stretching of the material and the curvature of the surface that we are approximating. And our goal is to move beyond developable surfaces, so which have zero Gaussian curvature because they're single curved. We want to be able to approximate also doubly curved surfaces, which have either negative or positive Gaussian curvature. And one attractive feature of conformal geometry is that the curvature of the surface is easily expressed using this logarithmic scale factor. And this is really not intuitive, but we can now nicely have the relationship between the change in the Gaussian curvature that is happening on the surface and the scaling that we need to have in our mapping from the flat domain to the three-dimensional domain. But the problem with our material is that the scaling configuration on the left, and we go all the way to the fully open configuration on the right, you can see that the material reaches its limit when it's in this hexagonal opening, and the scaling here is limited to 2 times in length or 4 times in area. So if you look at this triangle in the middle, it expands, the orange triangle, it expands to be 4 times larger than the initial one, than the one that we started. And this is actually our conformal scaling factor. It's limited to be between 1 and 2. Now, what does this mean in practice? So if we want to compute a conformal map of a target surface like the face of Max Planck that is 3-dimensional, we can get the 2D mapping or the mapping to the 2D domain that looks something like this. But the problem with this mapping is that in the region where you have the most curvature on the surface, that is the nose in this example, you will have the triangles to become extremely tiny. They will have to scale much more than 2 times in length. And luckily in computer graphics, we already did some work, and not only we, but Miri is an expert on this. You can reduce the scaling factor by introducing cone singularities. So how do you do this? You either pick a point or let your algorithm pick a point for you. And in this case, we would normally pick a point that is in the region of the highest curvature in the surface. And then we cut the surface all the way to the boundary so that once we map it to the 2D domain, it can propagate the curvature. It can push all the curvature or the error of the scaling towards the boundary because the boundary is now larger. And then the scaling factor will end up being lower than initially if we wouldn't introduce the cone singularity. So in this example, only with the 1 cone singularity and this 1 cut that goes from the nose to the chin, we reduce the scaling factor to be below 2, which is something that we need for our algorithm. Now, how does our algorithm actually work to approximate a surface? We start from the target surface and then we compute a conformal mapping, as you saw, to get it to the 2D domain. Then we can overlay a regular grid of triangles on top of this 2D domain conformal map. And we can use the inverse conformal map to lift this regular grid of triangles back to 3D and do additional optimization to make this into an auxetic material. So what is the additional optimization that we need is to make sure that these triangles now, because we just changed the topology of our regular grid in a way that it has the connectivity of auxetic materials. And we want to make sure that these triangles are going to fit the reference surface. So they are going to be mapped as close as possible to the reference surface. And this is especially important when you're doing conformal mapping in discrete scenario where you can accumulate a lot of errors. So in the continuous domain, conformal mapping works almost perfectly, but in the discrete domain, if you have large triangles and you're computing a conformal map, there will be some error in the lengths and so on. So we want to make sure that our triangles are fitting nicely the target surface. We also want to make sure that the triangles are all identical across the whole mesh. and that there is no collision between the neighboring triangles, which can happen once you're optimizing these triangles and you're mapping it around the surface. They want to squeeze somewhere and they can have collisions, but we prevent that with this additional constraint. And we can control all of these with weights, because sometimes designers care more about one of these constraints, and they can nicely control it with simple weights. Now you may think why we even needed conformal mapping at first place. If we can just throw this optimization equation at it, it seems like it solves everything we need. It is going to approximate a surface. It will be fabricable. There will be no collisions, and the triangles will be identical. But that is exactly how we model this example with only these three constraints. And the reason why it fails so badly is because this equation or this optimization that we are throwing at it is nonlinear, and it really depends on how you initialize your solver, whether you will get something reasonable or not. And that's why conformal mapping really plays a crucial role in our algorithm. And finally, once we finish the optimization, we get the result that is the one shown on the most right here. And if I zoom in, this is the approximation of the face, which is not too bad, but we still have some issues that are here shown on the chin, or where the cut has happened in the conformal mapping. And in many applications, this can be troublesome. If you need to preserve the stability of the material, you don't want to have these disconnectivities. But also, if you're working in something that has to be visually pleasing, this doesn't really look nice. So we want to have the continuous approximation of the surface that has no irregular cuts or holes in the approximation. And the way to deal with this is that we discovered that auxetic linkages, in order to preserve the topology across the whole linkage, the connectivity, if you have a singularity, it has to have an even number of triangles involved. So it cannot have 5 triangles, for example. It has to have 4, 6, 8, and so on, but it has to have an even number. And what this means for cone singularities is that they need to be an integer multiple of 2 pi over 3. So they can be a minus 2 pi over 3, plus 2 pi over 3, 0, but they cannot be anything else. And to compute the map that will help us deal with this, we then just use the quantized cone singularities. Well, so basically what this means, we prescribe the opening angle of the conformal map to be 2 pi over 3, or an integer number of 2 pi over 3. And now the regular triangular linkage can nicely align with this opening. So once we lift this linkage up in the 3D surface, it will be seamlessly connected across the whole cut that happened in the conformal mapping. So this was really crucial in order to make seamless connections of the auxetic materials. And to show some more examples of how the algorithm works, so here is the famous cat head, very popular in graphics. Here we needed to introduce, because the scaling factor is very high in the conformal map, we needed to introduce 3 cone singularities that are all quantized cone singularities of 2 pi over 3. So 1 on the tip of the nose and cut it to the bottom, to the neck, and then 2 on the tip of the ears, where you have the most curvature happening. And once we cut it out, we get this totally non-intuitive layout. If you were a designer and just manually trying to figure out what is the 2D layout you need from your material, I doubt that you will be able to get to something like this soon. And yeah, on the right, you see the final product, that is the cat head. And to verify our approach, whether it actually makes sense in real life, we fabricated some prototypes. First of all, related to the question from before, can we make the mask of Max Planck, the face of Max Planck? And this is the conformal layout, the 2D layout that we need. This is an actual piece of copper that is etched with a regular pattern of slits we need for auxetic materials. And the layout is computed with our algorithm. So otherwise you wouldn't be able to guess that you really need this opening in the 2D material to make the face of Max Planck, and that this point has to align with the tip of the nose of the Max Planck. We also 3D printed a face of Max Planck just to be able to guide our making of the auxetic surface. And here is the final result. So these are not the renderings, these are actual photos of the final product. And this is made with copper auxetic material. Another example we did is this high heel shoe. Why not? So we took a sheet of aluminum and we inserted a pattern of slits to make it auxetic. We computed a conformal map, the 2D layout that we need. We cut out the 2D layout from the aluminum sheet. Then we have to manually deform it, so open it, get all the opening angles to be what we computed in our algorithm. And we also 3D printed the heel to make the final product. And this is the video of the final result. Again, this is not the rendering, it's an actual physical artifact. And I'm sorry about the blue color popping up. This is something new in Keynote, why I decided to go for PowerPoint, but it didn't work out. One more example is this fabricated dress or shirt top, you call it as you wish. This is the 2D domain that we compute with our algorithm. And because of our global optimization approach, we are able to compute the approximation that has no seams wherever we have to, because the shirt is not a disk topology, and to be able to make it flat, we need a disk topology. With our optimization system, we were able to compute the global continuity across the seams, which is the blue thing happening on the side. And you can see that the topology is preserved of the linkage, and the same goes for the top part over here. The topology again is preserved of the auxetic linkage. And another interesting feature of these materials is that they are actually deformable. So from exactly the same piece of material, I can approximate many different shapes because I can control the openings of the triangles in different regions. And here what we show is how this mask of the Max Planck, the face of the Max Planck, is transformed to the face of my office mate, or actually ex-office mate, that has a totally different geometry of the face, but the same piece of material can approximate it just by controlling the openings in different regions. Now, this opens up many applications of these materials, like, for example, in the lighting systems, you can have a lamp that is fully closed everywhere. And then if you need more light in some regions of your room, you can open it up only in that region, or you can control where the light is directed in different part of the different part of the day, and so on. Or something like a facade system, so for shading systems, where you can have a computer-controlled facade, which will optimize the openings according to either the time of the day or the season or the weather prognosis or something like that. So you can have this facade be more open in some regions or more closed depending on the weather. And while this is a very nice feature of the auxetic materials, it's also in some sense a downside, because you have to have a really good control of every single opening angle to make it to the right one that was computed by the algorithm to make the final shape. Now we found a way to overcome this, and this brings us to these deployable structures, which are shape-shifting mechanisms that can transition between two or more geometric configurations. And deployable structures have been studied, for example, by NASA to put solar panels in the space, or designing heart stents to go into the heart of the patient and improve the blood flow. There's this famous Hoberman sphere that transitions from one state to the other, or actually a half sphere in this example, and also things like inflatable tennis court or football court, soccer court, that can be lift up temporary for the use and then easily taken down when you don't need it anymore. And again, what is the same for all these examples that we see here is that they're all limited to very simple geometries. They're either planar, cylindrical, or spherical, but not much more than that. And if somebody wants to design something that is like a freeform shape, it's not really something that you often see around. It's very complex. And again, our question was, can we make any kind of freeform shape or any kind of complex shape that has doubly curved regions, that has negative saddle points, negative Gaussian regions, and so on, changing curvature across the shape? And I hope I'll make sure you understand that we can do this. And now I'll dive into how we actually do it. We call this programmable auxetic materials. So what we are trying to do in them is to encode the target 3D shape into the 2D material. And let me just tell you how we design these materials. So quickly recall what are the regular auxetic patterns. So you have a bunch of identical triangles connected together, and they have this sort of locking behavior. Once they open up to the fully open configuration that cannot go any further, they just collapse back to the closed version. And in the uniform auxetic version, when you want to approximate a half sphere, to do that, to approximate some curvature of the surface, you are controlling the openings of the materials, but all the triangles stay identical. Now we said, why don't we go in the opposite direction? Why don't we use the material that has the same opening angles everywhere? So it's fully stretched, fully open everywhere, but we will control the sizes of triangles to be able to approximate the target 3D shape. And what this material will then look like in 2D, it won't be fully closed like before. It will actually be partially closed or partially open in some regions, but we will have the scaling of triangles different. So in the regions where we need more curvature to happen, we will have larger triangles because we will need more stretching there. And this is again related to conformal geometry that we will come back to. But in the regions where we don't need more opening or where we don't need stretching, the triangles will be small and they will already be fully open in the flat configuration. And by controlling the sizes of triangles, we are actually controlling how much the material can stretch. So what we are doing with this material, in each region of the material, we are controlling what is the maximal stretch that the material can achieve. And we say that the final configuration that we are getting with our material is when the material is fully stretched everywhere. And how we actually assign these scale factors? Well, again, with conformal mapping, because we already learned that the Gaussian curvature or the change in curvature that is happening in the material is directly related to the scaling factor, the conformal scaling factor. We can actually assign the sizes of these triangles based on the curvature that is happening in the surface. And that way we encode the 3D surface into the 2D material by controlling the local stretching of the material. But once we design this material, in order to make it really much better than the uniform auxetics where you manually have to open it up, we wanted a mechanism that will make the material to self-deploy or to be able to rapidly deploy by actuated with some mechanism. And for this, we figured that inflation and gravity both work very well, because what inflation is trying to do is trying to stretch it out maximally everywhere when you're popping more air in. And the gravity is also, if you hang it on something, the gravity is also trying to stretch it out as much as it can. But let me first discuss what kind of shapes we can make with it. Obviously, if you think of gravity, you cannot do whatever you want with it, or the inflation, you cannot make any kind of shape with it because you will be popping air inside. So what we learned during this process, and we were actually able to prove some theorems here, is that if we just simplify the inflation process to be just the maximization of the enclosed volume, and you consider you have some material that is limited in what area it can cover. So you know how much you can stretch it out, and after some point you cannot stretch it any further. So you have the limited area that you can cover with the material, and you're inflating it. So you're trying to maximize the volume inside. What happens is that if you continue inflating the surface on the left, this bump that was inside, it will actually pop out. So it's the way we characterize this in geometry is we say that the surfaces that have, if we define the mean curvature to be normals are pointing outwards, so the mean curvature is positive in the case on the right and negative in this region on the left, we say that we can only actually make surfaces with inflation that have positive mean curvature everywhere. And we were actually able to prove this in more detail. In the interest of time, I invite you to have a look at our paper to see more details about this and explanations. But basically, our conclusion was that once we have the limited stretching of the material and we want to maximize the volume inside, we can only work with surfaces with positive mean curvature. And this really informs our algorithm, how we can work, how we can approximate surfaces that were given by the user or the designer. So we first need to have a pre-processing step that will actually, once you get the target surface, like this Lilium tower, for example, it has this region with negative mean curvature. You need to transform it you either need to change the shape yourself, or our algorithm can transform it for you into the closest shape that has positive mean curvature everywhere. So just by editing the region where you have negative mean curvature, basically, this is just the top of this Lilium tower. And just not to think that the positive mean curvature surfaces are as limiting as the positive Gaussian curvature surfaces. We can even have saddle points, so we can have negative Gaussian curvature, but still have positive Gaussian curvature, mean curvature everywhere. So for example, here we have these saddle points, and now at first it has negative mean curvature, but once we deform it in these regions, it gets to positive mean curvature as well, but still preserving the saddle point, so still having negative Gaussian curvature. And just to show you some more examples of what we made with our design, so you can have, again, you can have positive mean curvature with saddle points. You can also have non-zero genus surfaces. And especially in this example, we also have had to use cone singularities, but again, in the interest of time, I'll invite you to have a look at our paper if you're interested in cone singularities here. Let's go back to the approximation of the surface algorithm. So the first part was about how you need to, what kind of shapes you can make and how you need to edit them, alter them to be able to make them. And now let's go into the second part, how we actually get our linkage. So again, we start with a target surface in 3D, then we compute a conformal map to 2D. We insert the cone singularities if needed. This surface luckily doesn't need cone singularities because the scaling is below 2. The conformal scaling factor is below 2. Then we overlay a regular grid of triangles. We use the inverse conformal mapping to lift it back to 3D. And what we do from here is that we, to initialize the optimization, we actually inscribe the triangles just by connecting the midpoints of the edges that were computed with conformal mapping. So starting from here, we just connect midpoints of each of the triangles to get these darker blue triangles, which is the initialization of our linkage. But again, because we are working in discrete world, not the continuous world, with our algorithm, we need to do additional steps to optimize this linkage to make sure that it's satisfying all the things that we need. So the actual optimization that we are doing here is of the 3D linkage. We need to make sure that the triangles are have expanded everywhere, that the triangles are equilateral or regular, and that they are nicely fitting to the target surface. And again, we can control all of these with weights. So the most interesting constraint here, which was different than the uniform auxetics, is this expansion constraint, which we were able to define nicely and in very simple geometric terms by using this Kramer's theorem that says that if you want to expand the polygon as much as you want, so you have the prescribed edge lengths of your hexagon, and you want to cover the largest area, because our triangles are of varying scale, so these edges are not going to be identical. It's not a regular hexagon, but we know the edge lengths. In order to expand the area that this hexagon is covering the most, these vertices of the hexagon need to lie on a circumcircle. So putting things simply, for our constraint and for our optimization, we can simply define a constraint that will say, well, we just need all the vertices that are forming the opening to lie on a circumcircle that optimization will figure out locally for each opening. And once we run the optimization, we get the shape that is the one on the right. So you can see the difference that the triangles were able to slide on top of the target surface, but also they changed the opening shapes and the shapes of triangles to be now equilateral triangles, and the openings to be larger than they were when we just initialized them with conformal mapping. And finally, to get the 2D layout of the linkage, we need to do one more step in the optimization. So we start from a regular linkage that has this connectivity of the auxetic materials. Then the simple optimization that we have to do here is we want to make sure that the edge lengths are matching the ones from 3D, but also that there is no collision in the 2D domain, which can easily happen because, again, this is a nonlinear optimization. So when the triangles are changing sizes in 2D, they can collapse and overlap and so on. So we want to prevent that by adding this additional constraint. And this is the final result that we get after optimizing 3D and 2D version of the linkage for our input shape. So this is the overview of the pipeline. The first part is related to conformal mapping, as mentioned, and this was really crucial in the whole work, both to the uniform auxetics and these programmable auxetics. And in the end, we had to do the optimization, but the optimization wouldn't work without conformal mapping. And to show again some results and some physical prototypes, the shape that we saw in the optimization pipeline, we laser cut the 2D layout computed by our algorithm. We then use the base on which we want to attach the material and then inflate it. And it has the opening hose for inflation. We then attach just the generic rubber balloon to be able to lift the linkage, and note that this rubber balloon has no information of the target surface. It looks totally different. And finally, we attached the linkage on top of this generic balloon. And this is the final result. This is actuated with inflation. So you see that the linkage is fully opening everywhere. And once it reaches the points where it cannot stretch anymore, it stops exactly to the target surface that we computed. If you recall the example from the beginning of deployable structures, now we can do a much fancier shape in 3D. So you can have this pretty looking tennis court, or for example, exhibition space, where you can also control the shape by the needs of the surface that you're building. Maybe you need more space in one region or higher ceilings, then you want lower ceilings in the other region of your dome. And this can easily be done with our approach. And again, it can be just inflated on site and go to the target surface with no additional construction work needed. Another interesting example we found with our that can be done with our programmable auxetics is that there is this somewhat recent work from 2016 where doctors have discovered that heart implants are currently designed to be regular cylinders, and this can actually be troublesome for some patients where the clogging of the blood vessel is happening where your blood vessel is actually curved. So what they have been looking for is curved balloons to be able to inflate these heart stents in these regions that are curved. And they only have, and they show the benefit of these curved balloons in the patients. But they only have been able to design the balloons and not the structure of the stent itself to be curved. And what we show here is that you can actually make a patient-specific heart stents by taking the scan of the patient's heart. Then you detect what blood vessel is affected, for example, this curved one here. Then we can easily reconstruct the shape of this blood vessel that we need to unclog. And this can be used as a target shape for our algorithm, which will then compute what is the shape of the programmable auxetics going to be, and it can be used as a curved heart stent to go exactly to the patient's blood vessel. So this is fabricated flat, and it can be curved into a cylinder, and then it can be compactly inserted inside, curved, and then inflated to the target shape. So you don't have to do anything else once you insert it inside except to inflate it. I mentioned that we were also looking into gravity as the deployment mechanism. I haven't discussed what are the mathematical backgrounds of it and what kind of shapes we can make. I invite you to look at that in our paper. But basically, they need to be, again, the positive mean curvature surfaces, and they have to be height fields in order to be deployed with gravity. So here we show one example of the target surface. This is the optimized linkage. This is the 2D layout of the linkage. And then because we wanted to make a larger construction, we laser cut the disconnected triangles, and then we connect them with simple book binders because it's a SIGGRAPH deadline. So you have to do it quickly with what you have. We assemble it on the ground, and this is around 2 meters by 1.5 meters. And the only thing we need to do is to hang it on the boundary, and it will go to the target shape. There's nothing else we do to inform the shape. So we are just hanging it on the boundary, and the gravity forms the final 3D shape. And this is the final result. So you can see that the material is stretched everywhere, and you can see these nice hexagonal openings happening everywhere. But still, we are able to achieve the negative Gaussian curvature, which again, to me, was non-intuitive when we started doing this, that this wouldn't fall down. But yeah, this is the final result. And again, I'm sorry for the blue artifacts happening on the video. We can also do multi-layered materials so that we close up all the surfaces. And again, because we are using conformal mapping, this cannot be done by simply overlaying 4 identical materials, but it actually has to have each layer optimized separately for the different region of the surface. And then thanks to conformal mapping, we can nicely align them in 3D and have all the holes covered. We also went a step further, and instead of just doing inverse design, we also did a forward design of these programmable auxetics so that the designer can actually locally adjust what is the curvature, what is the scaling of the material to get the target shape. So for example, you start from something like this, and then you say, well, I would like more curvature to happen here. So I will expand the sizes of these triangles by simply clicking on these triangles and assigning the new scale factor. And our solver will do this in the background. It will simulate what is the opening, and it will also smooth out the scaling factors across the region around where you edited the scale factors. And you can also get another surface by expanding this even more in different regions. And finally, you can use this for something like a simple shading system with 3 layers. Or the designer might want to be able to align the boundaries of the linkage. So here we prescribe this curve as a boundary and the circles inside as well. And the optimization will figure out how to arrange these triangles in order to fit the boundary perfectly. So this you can use, for example, for indoor cladding or Christmas decoration, or to hide the ventilation and so on in your building. And the only thing you have to do, you assemble it flat, you fabricate it flat, it's super easy for shipping and super fast for fabrication, and then you just hang it and it will go to the right shape. And another thing we can do is to, in architecture, these structural support are very important. So we can also assign the planarity constraints here, that we want to, these vertices that we assign in green here, to lie on the same plane. So that once we lift this as a dome or architectural structure, we can insert these vertical or these metal vertical beams that are going to support the whole structure in different regions that are needed. But the whole structure can be just inflated on site. And one going to real world with this, this is the shading pavilion that is planned to be built on EPFL campus next to the Rolex Learning Center. It was actually planned to be built 2020, but because of the corona and everything that happened this year, it was postponed. So we're looking forward to it happening hopefully next year if everything resolves on campus. But yeah, here we used hexagonal patterns, but still the theory is the same, and you just hang it and it will go to the right shape. And another interesting application we found with this is that you can use it to build habitats on Mars, because this can be nicely packed flat into your suitcase and brought to Mars. And because Mars pressure is 100 times lower than the pressure of Earth, the habitats needs to be pressurized. So you really want to have your dome to be inflated. But here you can have an interesting shape that will fit your needs for experiments and so on, but you can just easily carry it from Earth and don't worry about the construction on Mars. You just inflate it and it goes to what you need. And with this, I'll finish my presentation, and I'm happy to take any questions. I also would like to invite you to have a look at my webpage at MIT, because recently I've been doing some other stuff as well. I've shifted to machine learning and robotics. So yeah, if you're interested, have a look. Feel free to shoot me an email with any questions you have.